Hello and welcome to our podcast on the Pigeonhole Principle. We're Group B9 for EECS 203 in class on discrete mathematics. And for more videos in the future, please visit www.knoatom.com. So let's get started on learning about the Pigeonhole Principle. First, a basic illustration that everyone can understand. The basics of the Pigeonhole Principle is that if there are k number of boxes and you have k plus 1 number of objects, in this case, we have 6 boxes or 6 holes for 7 pigeons, then at least one of the pigeonholes has to have 2 or more pigeons. So I'll show an example illustrating that. So say each pigeon takes a distinct box. So with the first 6 pigeons, they go in each box, leaving you with a single pigeon. No matter which hole the pigeon chooses, whether it's this, or any, there will be at least 2 or more in each box. This could also work in other ways where there are 3 in one box, and so on. Pretty basic. So to define it, the traditional definition is if k is a positive integer and k plus 1 or more objects are placed into k boxes, then there is at least one box containing 2 or more of the objects, as shown before with the pigeons and the pigeonholes. Another example is if you have a deck of 52 cards and you're told to choose 5 of those cards, then according to the Pigeonhole Principle, the 5th card, no matter what is chosen, there will be 2 or more of the same suit. For example, if you have 4 cards are already chosen, and even if they're all distinct, 1 spades, 2 clubs, 3 diamonds, 4 hearts, then no matter what suit is chosen for the 5th card, then there will be 2 or more of the same suit for those 5 cards chosen.
Another way to think of the pigeonhole principle is with the generalized principle. The definition is, as you can see, if n objects are placed in k boxes, then at least one of the boxes will have n over k ceiling objects in that box. I'm going to show this with a proof by contraposition. Suppose that none of the boxes contain more than n over k ceiling minus 1 objects. Then you will have k times that number of objects. And now we can assume that n over k ceiling is going to be less than n divided by k plus 1. Because we can assume that, we can substitute that in right here instead of the ceiling function, and we also have a bunch of things that will cancel out. The 1's cancel and the k's cancel, which leaves you with this whole thing being equal to n. And that is saying that there are n total objects, which is not correct. Therefore, the contradiction is there and proves the pigeonhole principle.
So another example where cards are being drawn, except this is the more generalized principle, is the question asking how many cards must be selected from a standard deck of 52 cards to make sure that at least 3 of those cards are of the same suit. So as we illustrated before, when you draw at least 5 cards, that means 2 or more of the same suit. However, this question is asking how many cards are to be drawn to ensure that 3 cards are of the same suit. So in this case, as stated before with the ceiling of n over k objects, let's say there are 4 boxes indicating the 4 separate suits. And if there are 4 boxes, then there has to be at least n over 4 ceiling suits, or cards, sorry, in each box. In which case, we now know that at least 3 cards of one suit are selected, then n/4 ceiling has to be greater than or equal to 3. That's what we're trying to find out. So the smallest integer n, such that n/4 ceiling is greater than or equal to 3, would mean n would be equal to 2 times 4 plus 1, as shown from the definition before, and that would be 9. That would mean 9 cards would be sufficient to draw 3 cards of the same suit. This is because 9 cards must be selected. Well, in other words, 9 cards must be selected to ensure that 3 of them are the same suit. Another way to think about it would be that after the 8th card is chosen, then no matter what the 9th card is, there is no way to avoid having the 3rd card of the same suit. This is basically an extension of the original example where the 5th card, there's no other option but to have 2 or more suits, or 2 or more cards of the same suit.
This next example that we have is a little more difficult and has 2 cases to it, and I'll try to explain it the best as I can. The example is, it states, in a group of 6 people, there will always be 3 people that are either A, mutual friends, or B, mutual strangers. And you can assume that friendship is symmetric. If X is a friend of Y, then Y is also a friend of X. The best way to think of this problem is geometrically. Imagine the 6 people as points and let an edge between the points indicate friendship. So you have our 6 people, and if there's a line that connects one of these or 2 of these dots together, that symbolizes that they're friends. No matter how this is drawn, we just want to show that 3 points are all connected, or a set of 3 points are not connected. Basically, you're just going to consider any single point. There are 5 other points you could possibly connect to, and thus, by the pigeonhole principle, the point is either connected to at least 3 other points or not connected to at least 3 other points. And this will be shown in 2 different cases. Case 1, the point is connected to 3 other points. So here we have our 6 people. If any of these are connected to each other, then we have a mutual triangle of friendship, as you can see here, where each dot only has 2 lines leaving from it, so each person only has 2 friends, but there are 3 people that are mutual friends. And the other case is that the point is not connected to at least 3 other points. So again, we have our 6 people. If any of these points are not connected to each other, then we have a triangle of 3 mutual strangers. So again, if I draw the same picture as before, where we have the mutual friendship, there's also a triangle of dots that are not connected, therefore they are not mutual friends. Basically, this just shows that, it's proving that in a group of 6 friends, 3 will either be friends or 3 will be strangers. Thanks for your time. If you need to find more videos on discrete mathematics, please visit www.knoatom.com. Thank you.